We have a microphone. I don't understand why this is terribly relevant, because if anyone from outside this school does this assignment, I will eat my shorts. Show me, do it, do it. Find me someone else who will. No, no, no. Good luck. You're going to try to make a deal with someone outside the campus. Is it worth it? Have a look at the convergence if I change the damping parameter to 10, to 1/10, 0.1. So here it's 0.5, and I converge in about 20 steps. If I change my damping parameter to 0.1 instead of 0.5, it takes longer to converge. You also see some very interesting behavior in the convergence patterns. We can use alpha to try to detect local minima in our solution. We can see here that there are local minima here, 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 here. It is a very interesting probing tool. But we're not interested in the local minima, we only care about the final answer. So when you choose your damping coefficient, we need to be mindful that it will take longer to solve the problem, which for us is not such a big deal, because in our parallel computing course, we can show that the more parallel work we have, the higher the parallel efficiency. So actually having a small damping coefficient is good for our parallel efficiency, but bad for our speed. In COMSOL and many other commercial packages, you can modify the damping factor. So I know you can in COMSOL. I'm pretty sure in ANSYS and CFX you can change the damping coefficient to make a previously unstable simulation stable. For a pressure of 10, those are the answers. If we have a pressure of 10 coming in, the flow rates are about 1.09 and 1. They're almost identical, but they're not identical. And the total inflow is 2.09. Now you have to remember, this is an independent variable. This is an independent variable, and this is an independent variable. So you can use this to check your answer. If this plus this equals this, there's a very good chance that your solution is correct. And you can go through and check all of this. If you pick any arbitrary path, and you can see here, look at this. Look at the sign. I was wrong. The flow is actually coming out this way in this case. So there are many instances where these negatives are going to kill you. You lost your chance, man.
Hey, come on.
Nah. So you guys now know how to. The inflow was 2.09 and the two outflows were 1 and 1.09. I can tell you that. I'm not going to tell the other flow rates. It's on the freaking YouTube video, man. Just go on and get it. I know Tree is already there. Someone's already there. I was seeing, yeah, look at that. He's just watching now. You can go through and grab it now. So let's continue. Putting the assignment down for now. You guys have got enough busy work coming up ahead of you. Today is the last really valuable course. Next week, we're going to do something crazy hard. Next week, we're going to try and mix today's stuff with OpenMP. But today, I want to talk about this stuff. Now, what are we talking about today? Vector extensions. Vector extensions in modern computing actually means something called vectorization. Vectorization. When we optimize our C codes, when we're writing C codes and we use a compiler to compile, you guys might be aware of this. I'm telling you now. This here is what we call an optimization flag. Now, 我可以拜托你一下 when you finish your thesis, 如果你的 thesis 是跟计算有关 when you compile your code to measure the performance, make sure you use at least 02 or 03. Because this flag here has a massive, massive impact on the performance of your code. And today's class is to try to explain to you why it has such a massive impact, when it won't have a massive impact, and how you can guarantee the same impact in any code. So this is optimization. Optimization most of the time means vectorization. And vectorization refers to vector extensions. To understand what vector extensions are, what's the average age in this classroom? Man, that takes me back. I was thin and I had hair. And back then I had girlfriends and not wives, but that's fine. Back before you guys were born, we were using computers for work. Let's have a look at those computers. I want to look at the frequency of CPUs as a function of time. This list starts way back in 1985. I was alive then. I was in primary school, actually, a little kid, playing in the sandbox. On the left-hand side, we see the frequency of our CPUs. On the bottom, we see time. This is a logarithmic graph because the frequency is some kind of crazy thing which increased very, very quickly for a while and then stopped. My first computer, my CPU speed was 25 megahertz. It was a 386 enhanced SX25 created by Intel. It was awesome at the time, I thought, and my computer system had 4 meg of RAM. 4 meg of RAM, less than your phone by a long way. Then the frequency started to increase. As we decrease our die size, we increase power, we increase frequency. Everything was fine and dandy. And we see that our increase in frequency went all the way up to about 3. Didn't go much past 3. In my lab now we have the new server that operates at 3.7, which is a pretty good score, pretty good high speed, 16 cores at 3.7. Yeah, I'll take that, that's a good deal, but that was an expensive machine. But more or less plateaued out here. Now, wami or jangor jiga plateau. That's not what we're talking about today. This plateau occurred because the power was too high and we were starting to melt the CPU dies. We were eroding the electron pathways on the chip. So we couldn't go any higher. I'm talking about what happened down here. So on the very first SX25, that operated at 25 megahertz, you couldn't do anything. That computer was useless, man. I used to use it to play crap games, but even to make a simple game work, I was using DOS. I needed to use a boot disk, which meant I needed to edit the autoexec.bat file and config.sys file. I needed to choose which drivers I loaded, the mouse driver, the sound drivers, the memory drivers. I needed to choose a memory driver. I needed to load them in the correct order to save memory, and I needed to choose which memory to load them into. I was 10. All of my knowledge of computers is because I wanted to play games when I was a kid. But it really worked very well. To make our computers do anything back then, we needed to work hard. People don't like to work hard. And so technology evolved. Prior to 1995, every CPU you got had a single core and they were capable of computing 1 flop every cycle. So you get a CPU, a 25 megahertz CPU, which means that every second it does 25 million flops, million cycles, million operations. And in each of those, you can do one lousy computation. That is not a lot of data. There's not a lot of power to play games. You can do work. I used to have a Turbo Pascal editor. I used to program Pascal on this machine, but it was no good. If you're doing standard computing, it was fine. But as computers became cheaper, they started to find a wider audience, and people started using these computers to do different things. I started using computers to do different things. So my first computer was the SX25. It was an Oliveto machine, which meant that it was a business computer, and it cost $4,000 US. My first computer, I was 10, and my parents bought a $4,000 computer. My mouth fell open because my parents are broke. So I owe my parents about $4,000 bucks. Back in 1995, I was in high school and they started creating games like this. Does anyone know this game? CNC. In Taiwan, it was its sequel, Red Alert, that was famous. Taiwan Red Alert became popular, but before Red Alert was Command & Conquer. Now, Command & Conquer was made by Westwood Studios and was one of the most revolutionary games ever made. It's a complicated device. It's a complicated game. This was the first game where we had video clips and sounds and a lot of data to present. This was real-time processing and for an RTS game, very computationally expensive. At the same time, another little company that no one had heard of before called Blizzard. Who are these guys? Blizzard. Never heard of them before. They made a game called Warcraft. They made Warcraft 2 in 1995. I still have legitimate versions of both of these games. I actually really do have legitimate versions in addition to the other versions. Command & Conquer, Warcraft, cannot run on an Olivetti machine. They do not run on a SX25. The problem is they wouldn't run very well on any of the computers at the time because the single core, with a clock speed of, at the time, the best one was about 66 megahertz, was just not capable of performing enough computation. Because back in the day, there were no GPUs in these machines. So the CPU had to do the drawing work. So the CPU has a lot of work to do here. CPU also has to do sound. So while you're playing your game, CPU has to control the game, CPU has to do the graphics, CPU has to do the sound. It was very complex for the CPUs to do at the time. There were also other applications. This is, in case you haven't seen this before, Windows 95. If you want to see a Windows 95, go to the Tainan train station. Most of their computers still use Windows 95. I'm serious. Go check it out. Back when Windows was created, Windows was famous because Windows gave you the option to watch a video on your computer. And this was revolutionary. When I was a kid, you could not use a computer to watch video. It was impossible. But when I was about 11 or 12, we started using computers to watch video. And I got my first encyclopedia on a CD. When I was a kid, you know what an encyclopedia is, right? It's like many, many books that contain subjects on a wide matter of topics. And we used to have these encyclopedias, and people used to buy libraries of them. I had a small encyclopedia set, but when I was 11 or 12, we got a CD which had an encyclopedia on the CD. It allows us to play media. Windows 95 was one of the first operating systems. Windows 3.1 was the first one, but Windows 95 was famous for its ability to play media. And it used something called the Windows Media Player, which in 1995 was version 7. The Windows Media Player that you guys use now on these machines is like version 86. It's incredibly evolved, but it all started here. Windows Media Player can do a lot. It is able to stream video, is able to do real-time compression of music and video, and it's able to extract compressed video and music. MP3s are just one form of compressed music. So I remember when MP3s were invented. Back when I was a kid, they were too complex for a CPU to decompress in real time and play. You need to decompress sections and load it into memory, then play it. Wow. So what happens? People liked devices which worked. That's what I want. A clicker that works. People liked Warcraft 2. That was actually a very famous game. People liked Command & Conquer. Both of these companies became extremely rich. Well, the company that made Command & Conquer was purchased by another evil organization. Do you guys know who that is? Electronic Arts. Perfectly legitimate company. And Blizzard is still Blizzard. They made World of Warcraft. I'm not sure, and Diablo. You guys might have heard of Diablo 3 before as well. Diablo 2 was famous in Taiwan because there was a cracked version that went everywhere. So, all of these programs are very dependent on graphics operations and music, sound operations. Sound and graphics computations are SIMD computations. Now, if you remember, SIMD is single instructions across multiple data. SIMD, single instructions across multiple data, means that we are able to perform parallel computing on these operations if we have the computational power to do so. But the problem was the computers at the time only had one core. We couldn't parallelize. We couldn't parallelize by adding more cores. The technology wasn't available then because the first multi-core CPU didn't come along until the early 2000s. And this is before then. This is an example of a code that performs an SIMD computation. This function here is called compute ordinary. We iterate over n elements, and in each element we add these two vectors together. This is a vector addition. This is just like the streaming operations we do on the computer when we're unpacking music, just like the graphics computations, only this is a very, very simple example. Why is this called a SIMD computation? One, we have n elements, so we have multiple data. But the instruction C equals A plus B is the same instruction for all n elements. So because we have a single instruction performed over multiple data elements, this is SIMD. Now, CI is a function of AI and BI. 这个 ith 的结果 only touches I. So I, 不管 I minus 1, 不管 I plus 1是多少 I 只要看 I. Which means that we can break this loop up. We can parallelize this loop. We've done this before on the GPU. In the GPU, when we want to do this operation, we assign one thread on the GPU to do all of the computations. Each thread manages one of these elements with n elements, so we need n threads here. And that allows us to parallelize our computation and get very high speed. I want you guys to write down right now a simple C code that performs this computation. Because the next step, I'm going to show you after this how Intel came up with a solution to the SIMD computation problem that we faced in the 1995 times. Write this down. The actual full source code is here. If you want to take a picture now. This is a baby code. It's an easy one, but if you want to take a picture and then print it out and put it next to your bedside stand and you can see it every day when you wake up, knock yourself out. Run. All right, let's keep you guys busy before you fall asleep. Here we go. This part's going to rock your world. Back in the day when we had computations like this to accelerate, we didn't have multiple cores and we didn't have GPUs. So we couldn't use OpenMP and we couldn't use CUDA. So Intel created something else. It was all Intel back then. The thing that Intel created is the single thing which is responsible for most of the money they've made since. This is what made Intel really famous. Because what Intel used to make were the small chips that go inside your washing machines and dishwashers. This was a time when Intel created a technology which gave them an edge over their competitors. And this is when people started using Intels for personal computers, for PCs. They created something called MMX. MMX was a big deal at the time. Here's the MMX logo. MMX, if you Google MMX and ask Wiki what it is, actually it won't be able to tell you if you look for the definition. Back in the day, MMX were called multimedia extensions designed to support graphics and sound and video, which is why they called it multimedia extensions. But I'm pretty sure that by calling it multimedia extensions, they violated a patent from another company, and so they denied that's what it was for. But that's what it stood for. This is when Intel started to become quite powerful. Now, I haven't told you what MMX is. Inside each CPU, there is an ALU. The ALU is the mathematics part of your CPU. It is the part of the CPU that does the calculations. What the Intel engineers decided to do was modify drastically the ALU in these CPU cores. They decided that they would find a way to add a parallel computer or a parallel computing register into the ALU of the old Intel chips. This is what MMX is. So this is a Pentium 4 diagram. Pentium 4 was introduced at the beginning of this century. One of the best chips you could get at the time. The remnants of MMX are still here. Here's our ALU. ALU does all the math inside our computer. This section of the ALU is called the SIMD register section. This part of the ALU is capable of performing parallel computation. Now, we have one core here. No GPU, just one core. And yet we're performing parallel computation inside the chip. Because the Intel engineers designed SIMD registers. These SIMD registers are a special place, a special way of lining up data in memory and special processing capacity to allow multiple floating point units to be computed on each cycle. There they are. What does this really mean? It introduced a new type. 到现在你们所有用的都是 float. A float has 32 bits. Maybe use an int. Int is also 32 bits. Intel introduced a new type of variable called the MMX variable. The MMX variable at the time was a 64-bit variable. But inside this variable was not one variable. It packed 4 half-precision integers. By taking one variable that packed 4 half-precision variables, we can then take these variables, pass them on to our SIMD register. The SIMD registers are designed to perform computations upon the MMX variables. So every time this register performs one operation on one of the MMX variables, it believes it's computing one result, but it is not. It is computing the operation upon 4 half-bit integers. So in one cycle, we are using these registers to compute our operations on this MMX variable, but by doing the computation, we're actually computing across 4 elements. 所以以前我们每个 cycle 可以做一个计算，现在每个 cycle 我们可以做4个计算。那其实我问你，那个 half precision integer 是什么用？以前 it's very, very good for graphics and sound. Graphics and sound at the time were using half-bit half precision integers. 现在我们都是 AI. AI uses half precision variables. Very, very important actually. We can use half precision variables in these MMX registers. But at that time, no one was using MMX registers to do half precision AI computations. It was all for graphics. That's what it was designed for. Keep going, come on computer. So, the moral of the story is by packing our data, by packing 4 half precision integers into one variable, we can take these variables and perform a single operation on them and get a single result that contains 4 results. So we're performing the same computation on all of these operations, on all of these elements at the same time. So we can see here, there's a reason why they call these the SIMD registers. These registers are performing single operations on multiple data elements. So that's why we call them SIMD elements. MMX at the time could only operate on 4 elements at once. And all of the operations here were simple operations like add, subtract, times. So they were no good. So the restrictions were the original MMX, this 64-bit register here, the 64-bit variable type, the MMX variable type, inside was packing 4 16-bit variables. All of the MMX operations must be on those 4, must be on that type. They must be integers. The same operation must be performed across all elements. This is SIMD. So because the SIMD engine takes one MMX variable which contains 4 elements and does one computation, that computation is done to all elements. 一个计算应用到所有的 elements. And the data must be stored in memory in a special way. This is the kicker. This is a surprise. At the start of this course, you guys were allocating arrays by saying float A10. That placed arrays in a horrible place in the machine. Then we started using malloc. Malloc seemed okay. We started using CUDA malloc. CUDA malloc is quite different to malloc, the way it stores memory. But now, I'm going to tell you right now, malloc is not an acceptable tool for memory allocation for high-performance CPU computing. And I'm going to explain why. If we're going to take advantage of this kind of SIMD computation, we need to prepare our memory allocation in a very special way. Malloc and stuffing arrays onto the stack are not going to cut it. I'm going to talk to you a little bit about why that's important. But first, SSE. SSE came after MMX. So Intel, after having invented MMX, made a fortune. They turned from a small company that no one had heard of into a massive operation. It was about that time when you started seeing Intel selling a lot of CPUs, and it was at that time they started selling the logo that goes ding, 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 ding. That one, you know that one? I'm terrible at sound effects, I'm sorry. Sorry, not sorry. That was MMX. But MMX had 64 bits, per MMX variable that packed 4 floating half-precision integers. 谁要用 half-precision integer? Not many people. For graphics, for easy graphics, it's fine. But once we start going to advanced graphics, it's not fine. It's the opposite of fine. We need something better than that. And right now, the standard for graphics is single precision floats. That's what GPUs are designed to operate at. So we needed a system to store floats instead of integers. Now floats are 32 bits. Intel was storing 4 half-precision integers. So if we're going to successfully store floats and take advantage of the computational power, we need more than 4 half-precision integers. We actually need to do 2 things. We need to be able to fit floating point variables in, each one being 32 bits, and we need to squeeze them into a 128-bit register. So the SIMD register length changed from 64 to 128. When was SSE introduced? 1998 or 1999? You guys can Google it. But it was a big step because we're moving from 4 half-precision integer operations to 4 floating point operations. This is good for games. this is good for everything else. If you're writing an engineering code and your code is not taking advantage of this power, you are going 1/4 the speed you should be. Because in a normal code, you can perform one floating point operation each second, each cycle. By using this system, we can perform 4 floating point operations per cycle, not 1. It's a massive increase in performance. And the first CPUs that introduced SSC were very powerful machines. But at this time, it wasn't just Intel. Intel worked with AMD to introduce SSC on all CPUs. So nowadays, you buy any CPU, it contains SSC, with the exception of ARM. ARM cores now use another vectorization mechanism called Neon, which I can talk to you about if you want to outside of class. That's what this whole class is about, son. How fun. I know it's annoying, right? That's life, man. Yeah, life sucks. So let's provide you guys with a concrete example, because I want to show you exactly what it is. Let's say I want to add four elements together from 2 arrays. We have 2 arrays. I'm going to tell you about how you can automatically use it. And I'm also going to tell you how it sucks. You're going to discover on your own today. That's what the mission is. We have an array. We want to add these 2 arrays together. To do this, we pack them into 2 SIMD vectors. This variable is called A. This array, is called A. Array holds 4 values. They are stored in the XMM registers on our machine. We're going to take the elements from these and add them together, a vector add, because we're going to perform an addition across this vector and produce this single result. Because this result only depends on this, and this result, for example, only depends on this and this is a pure SIMD operation. So it is perfect for vectorization. So how do we make this work in SSE? First up, we take our array A. Now array A here contains 4 floats. We transform it from an array called A holding 4 floats to a special array called SSE-A. SSE-A contains 1 variable. That variable is called SSE-A, and it is 1 SSE type float of length 128 bits. Inside is 4 floats. Inside are 4 floats. SSE-B also is 1 element, 1 SSE type variable that contains 4 floats inside. Now when we take SSE-A and SSB and we add it together, we get SSE-C. It is also an SSE type variable which contains 128 bits, packing 4 floats. And I've already shown you the answer. We perform an element-wise addition on these elements, so 3 plus negative 0.1 is 2.9. You can see how all of the elements are vector operated, vector added. So in order for us to use SSE, we need to take our floating point arrays and then pack them, transform them into SSE type variables. Step number 1. There's something you need to know before we go any further. A is an array containing 4 floats. We can print the contents of A, can't we? 我们可以用 printf 给我们看一下，如果我们要看第一个 A， 那我们就说 printf A0 就会有办法看到。Can we use printf on SSE-A? SSE-A is a special variable that holds 128 bits of data, 4 floats. If we try to use this with printf, when we want to print a float, we type %f or %g, right? If we want to type an SSE variable, what is it? %nothing. You can't print them. They are specially prepared packed data types. You cannot print SSE types. You need to unpack and then print. It's not hard. After the data is packed, we need to use a special function to add these SSE variables together, because this function here is a special function which is designed to work on SSE type variables and only SSE type variables, not regular variables, because we're performing elements across all of these types. The functions which perform these vector operations are called vector intrinsic functions. And they are very, very powerful tools. In this case, we're performing a vector add. So how do I find out what that function is? We're going to get to that. Once we find out what this function is called, it's going to produce SSEC. It's going to give us one SSE type or 4 new floats inside that SSE type. We can't touch SSEC, but we're going to align memory in such a way that we can access C here, which contains our answer. And you'll see when I give you the code. Yeah, go on. Before I go any further, because it's about this time where someone asks me, isn't there any way that the computer can automatically do this kind of work? I've got a crystal ball at home. I just mistimed my slides by about 2 minutes. The compiler is able to, in a limited capacity, able to detect instances where data can be operated upon using SSE intrinsic functions. It can. The code is capable, the compiler code is capable of looking at your code and saying, oh, there's a for loop here. Each for loop only operates upon its own element. We should be able to vectorize this. And it does. Half the time it works. The other half it does not work. And it is difficult to check. My mission today is to show you how to check to make sure it's worked, because it's important, because it will influence your performance. If you think you're using SSE but you're not, you're going 4 times slower. 4 times slower is a big deal. 4 times faster is a big deal. If we're going to try to use automatic vectorization, it is done using the O3 flag and the O2 flag, as a matter of fact. O2 will also attempt to do it. So when we use this flag, like you just did, if you go into the machine code for the code that you just compiled today, just before, you should be able to see that you are taking advantage of SSE if the bloody compiler did its job. Now, let me use my magical powers to predict the outcome. It didn't do its job. It didn't work, and we're going to show you why. The compiler is not an intelligent device. It tries to be. Unfortunately, compilers were written by people, and people are stupid. People make mistakes, and so the compilers make mistakes. Because the compiler makes mistakes, even though we try to make it intelligent, it often makes mistakes with its automatic vectorization. Sometimes this the mistake in automatic vectorization causes your code to have a segmentation fault when you did nothing wrong. Your code works perfectly, but your code crashes when it runs. It's not your fault. It's the compiler's fault. It's not an easy trick to find out who was responsible for these errors. I'm going to show you how we do it. Now, we can make a mistake, blah, 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 blah. Instead of relying upon the compiler, we're going to manually set up these intrinsics. Today's mission is for you to write a code. You guys are going to manually write the intrinsic functions. Then you're going to compare the code to the automatic vectorization. You're going to be able to look at the machine code. I'm going to show you how. And you're going to be able to analyze that code to see if it is properly using the SIMD registers. Fortunately for you, the code is very easy. There are only a few steps. Allocating memory is the first step. We need to find a special way to allocate memory. The funny part of today's course is most of you today are going to use the ordinary malloc function to allocate memory, and it is going to work. For most of you. Maybe in this class there will be one person that gets a segmentation fault because they used malloc. I'm hoping that will happen today, because malloc is not suitable for SSE computation. It causes segmentation faults unless the computer memory is very large. My computer memory is extremely large, which is why there's a chance that none of you will see a segmentation fault. But I need to prepare you for it, because when you run your code on your machine, which may not have as much memory, you're going to see a seg fault. Allocate memory in a special way. Pack memory from the regular 32-bit to 128-bit SSE types. This sounds like a lot of work. It is one line of code. C is designed to do this quickly and easily. It'll be so fast, you'll be amazed. Once we've packed our memory from 32 into 128-bit types, we use SSE intrinsic functions to perform our math instead of regular plus and minus operations in C. How do you find out what those functions are? Google Intel Intrinsics Guide. If you Google Intel Intrinsics Guide, it will give you an interactive website which allows you to search for the intrinsic functions, because this is big business. If you have a way of accelerating your gaming computations 4 times, you have a way of making your game run 4 times faster, your FPS will be 4 times higher, and you're going to make a lot of money. The entire gaming industry relies upon this website. Except mobile gaming, because they need Neon intrinsics. But for the rest of the gaming world that use PC or even PS4 and PS3 and Xbox, we need these intrinsic functions to work. This is what the website looks like. Now, we want to, let's continue the code that we were looking at. 我们刚才要做一个 vector add. We need to add 2 elements together. So we need to perform an addition operation. And today we want to use SSE. Not SSE 2 or 3 or SSSE, special SSE, or SSE 4 or SSE 4.2. Just regular SSE, please. So we click on SSE and we search here for add. If you search for add, if you follow the instructions I just gave you, this is what it looks like. You get this result. The function you were looking for is here. Underscore underscore. 我很喜欢这个空间。你看到这里有一个空间吧？很好用。There is 2 underscores here. 请你不要忘记这个很重要的东西。Underscore underscore M128. What the hell is that? MM128 is an SSE type variable that contains 128 bits of information. We don't know if it holds 4 floats or 8 half-precision integers or 8 characters, half-precision characters, or double-precision characters, sorry, long characters. All we know is that it stores 128 bits of information. This function is it's called this underscore, single underscore, mm underscore add ps. Add is a fancy way of saying add. PS is a parallel add. We add A and B. The input into our function must be another SSE type. So we're taking 2 SSE types and producing another SSE type, but inside each SSE variable, today we'll be having 4 floats. So by using this function, 我们有加速，有让它变成快了10倍吧。By using this code. Here's our function. The SSE type C is actually the MM128 underscore underscore M128 type SSE variable. And that's its name, and we give it another SSE type and another SSE type. Yeah. There's the code. Now I want you to do 2 things. First, the code that you just wrote, please do not just change that code. I want you to keep that code because we're going to analyze the differences later. Take the code you just wrote now, save a copy of it, and then chuck this function in there. This is the SSE accelerated equivalent of our compute ordinary function. And there are some differences between it and the code that you just wrote. Write down this code, please. You're going to discover that you do not need to add this, as a matter of fact, because SSE is so common. Everyone in the world uses SSE. G++ is going to assume that you are as well. But chuck it in anyway. Please include xmmintrin.h at the top of your code. Make sure you save a copy of your original code as a different file so that we can come back and check the codes later, compare them. Hang on. Wait. You guys ready? Have a seat. 先坐一下. Let's have a look at this. I want to talk about how this thing works. You ready, Alex? Because I'm starting. The compute SSE function has two parts that you really need to know about. The first line, which is really important, actually the very first line, which is really important, is that n SSE equals n divided by 4. Why does our for loop iterate over n on 4 instead of n? 我们以前要跑这个 for 的计算，我们是用 n 个 elements， 但是我们现在没有用 n 个计算，我们只有用 n on 4. That's right. Every SSE function. Sorry? Every time we call that SSE intrinsic function, we pass it 4 floats. So we perform 4 less operations. So 这个 code 应该是快了4倍吧? It is in theory. That is why we divide by 4. 如果你忘记 divide by 4, or you leave it as n, or you multiply it by 4, who would do such a crazy thing? You're passing it too much information. You're asking it to iterate too far. Because if we have n elements, we pack these into n on 4 SSE variables. So that's why we have this. Here is our SSE type variable declaration. These, because A, B, and C are arrays, we need arrays of SSE types. So we create floating points. But, check this out. This is an array of SSE types. Do we use malloc to allocate memory associated with those? Normally when we create an array of floats, we declare the pointer, float A star, or float star A, sorry. Then we use malloc to allocate the memory. Here I create my types, M128 star SSEA. So I have a pointer to memory of type 128, but I don't declare memory. I don't allocate memory because my memory is already allocated. The memory I want to use has been allocated in regular ABC by malloc. What I need to do now is point my SSE variable, my SSE pointer, to where my A, B, and C are. It is not so easy because they are different types. A is type float, but SSEA is type SSE, 128-bit. So I need to perform a forced type conversion. I need to force a conversion between a floating point array and the 128-bit element array. This sounds complicated. It is not in C, C++. When I point my SSE type pointer at the A matrix, at the A vector, sorry, all I need to do is point it directly to A, and I used a forced type conversion. And in C, our forced type conversions are performed in this way. I'm hoping that you guys have had some experience in forced type conversions when we change integers to floats by putting bracket float in front of the integer. In this case, we're doing the same thing here. We're forcing this to be allowed to point to A by doing a forced type conversion. So SSEA, SSEB, SSEC are not separate places in memory. They are pointing to, they are overlapping the areas in memory for A, B, and C. But each time we look at one piece of SSEA, we're actually looking at 4 elements from A. Once we've pointed our A, B, and C for SSE to these variables, we are able to use them. We say SSEC is equal to MMAddPS, that's our intrinsic function there, and then we pass SSEAI, SSEBI to that function. After we've run this, you're able to, in your main code, print F and look at all the values of C. I never set C, did I? Did I set C here? Like in the previous code in compute ordinary, we said C equals A plus B. Do I touch C here? I touch C by touching the SSE variable. SSEC is over the top of C. If I perform a computation on SSEC, because the memory pointer is pointing to A, the results from SSEC are placed into the C matrix, sorry, the C vector, not A. So when this computation is complete, SSECI is going to take one SSE variable and place it in the ith element of the SSEC array. And inside that is going to be 4 floats, which are occupying a space inside the memory that is occupied by C. 所以这个 code 没有more C， 没有more 少 C， 我们这里只有 more SSEC， 但是因为它们是 pointing to the same spot, when I change SSEC, I'm changing C. That's what makes this possible. This is quite tricky work. The method that you see here is called packing. I don't need to unpack because my data is well aligned. This is called packing. Well, sorry, this line is called packing. Now I'm able to perform packing in this way under the assumption that my memory is properly aligned. Now what does that mean? We'll come to that. So we've asked this question before. Why do we use n on 4? We use n on 4 because every SSE type has 4 elements inside. Piece of cake. Go on, fast. Now, let's do it. How do we know if this code is going to run properly or not? That is going to be an interesting trick. How do we know that this code, the one that we've just written, is properly using SSE? We perform an object dump. Let's say your code is called main.cpp. We want to deconstruct the object so that we can see the machine code. I want to see, we need to go to the very lowest level of this thing to make sure it's working properly. To look at the machine code, I need to create the object. Then I need to do what we call disassembling. I need to disassemble my object to create a machine code. So to get my object, hey, what does this symbol mean? Look on your keyboard. Enter. Just making sure that you guys know, because people have asked me before, where do they find this symbol on the keyboard? Actually, you can find it most of the time. It should be quite easy. This creates an object. This creates the main.o file. Now, that is not an executable. 那个不可以跑，那个就是一个 object file 而已. But inside the object file are all the instructions the computer needs to run it. If I want to break it down, I take this file and I perform an object dump. The object dump in Linux is called by using this. Object dump. Then I write my file down. Then I need to tell object dump what I want to do with this. I want to disassemble. That's a terrible D. There we are. That's a terrible D. That's the D I'm looking for. Compile the object for the code that you just ran, please. I want you to find, once you do this, once you compile your object, create main.o, then perform an object disassembly on that file, you will see this kind of crap. You will see a massive file, a massive amount of information for every function that you write in your code. There'll be main, there'll be init, there'll be compute ordinary, and there'll be compute SSE. Because your code has compute ordinary and compute SSE in the same code, probably, then you are better able to compare what these things look like. This is how we know if our code is working or not. Once you type this, you'll see a massive list. You'll be able to check every function that you've got in your code. If you do it properly, your code should look like this. Now, my SSE computation, this is machine code. We want the machine code to be as small as possible. If the machine code is small, there's a good chance that the computational load is small. Not necessarily true, but there's a good indication that a simple machine code is going to perform a more efficient computation than a complex one. My compute SSE looks like this. I wonder what the other one looks like. Here we are. This is the compute ordinary function. You will see that your compute ordinary function is a massive beast. You have such a simple code, but yet your machine instructions are very complex and numerous. The compute ordinary code, even though it's such a simple for code, is very large. It doesn't necessarily have to be large if the compiler succeeded, but then we have to analyze it carefully. Right now I'm just checking for size. Your intrinsic function that uses SSE intrinsics, compute SSE should be smaller than your compute ordinary code. If it is not true, that means there is a chance that the compiler has succeeded in properly optimizing your compute ordinary function. But we're not finished yet because we need to make sure it's doing the correct thing. Before we move on too far, I just want to summarize what I just told you. By using the compute SSE function, which uses SSE type variables, and we perform an iteration over n on 4 elements, we have substantially decreased the size of our object file, and we are producing much more efficient code. Your code will run many times faster than this. So you can see, you might think that this code is going to lead to the optimal machine code because it's a simple code. Unfortunately, life is much more complicated than that. It's worth you knowing what is in your machine. The reason why our SSE code works so fast is because SSE forms a key part of the way your ALU operates. Now, all of the CPUs you're using today are Intel or AMD. They all have ALUs with SIMD registers inside. By writing your code in this manner, we are not helping the compiler to do the vectorization. We are making it do the vectorization. We are forcing it to do the vectorization. So it is giving us the best possible machine code. In this code here, the compiler attempts to perform the vectorization, but because the compiler is not smart, it doesn't know the best way to do it and makes mistakes. By comparing these things, let me see. Actually, in this case, it didn't succeed in performing the vectorization. Oh, sorry, it did. This code does do SSE vectorization. You can actually see because we have add PS in the XMM registers. So we are operating in the SSE register area and we are performing additions in parallel. So we're here. See? Add PS using the XMM registers. We are performing the same computational work. Both codes use SSE. So the compiler in my example succeeded in using SSE, but look at this mess of shit. The compiler have you guys ever tried using the MATLAB compiler to take a MATLAB code and make it into C code? It can do it. The C code it gives you is the filthiest, disgusting, ugly C code you have ever seen in your life. No offense to MATLAB or anything, they do a fine job and they try their best, but they fail. The compiler here has succeeded in automatically vectorizing the work. Congratulations. But this is not beautiful machine code. This is a waste of time. This is fantastic compared to the compiler effort. Let me tell you the conclusion. If your compiler succeeds in doing the automatic vectorization, it is still going to be between 5 to 20% slower than your own code. If you want the fastest possible code, you guys are going to write your own intrinsic functions. This is the way to go as fast as you can. Now, why is this important? Why am I teaching you this? It's very important because I'm teaching you how to do GPU. You guys are learning how to do GPU computation. You're going to use GPU in your thesis. You might even have a chance to go to an international conference and present your GPU performance. Inside the audience, there's going to be one person who says, how do you know when you compare your GPU code to your CPU code that your CPU code is going as fast as it can? This is the way to do it. If you want to compare your GPU code to CPU and you really want to know how much faster GPU is than CPU, you must do this. This is the only way to test how powerful the CPU is. If you rely upon code like this, it is not going to be properly transformed into machine code. And the code you get will be slower. And it will make your GPU look fast. And that makes people angry. And it happens every time there is an international conference. So this is why I teach you guys this, because best practice demands that if you're going to compare GPU and CPU, you need to take the fastest GPU code and the fastest CPU code. 只有这个公平的方法。如果没有用这个公平的方法, why even bother doing the work? You have to use intrinsics to know. Every major commercial package uses intrinsics. COMSOL, ANSYS spent millions of dollars making sure their codes were written like that because they want to make sure their codes run as fast as they can on the equipment they have available to them.
So now we run SSE, what about the other functions?
Sorry?
What about SSE 4.2 and stuff?
I'm coming to that. After I talk about memory first, if you don't mind. Unfortunately for me, it seems like everyone's code here ran perfectly. I hate when that happens. I was really hoping for a seg fault that wasn't someone's fault. Instead, I got a classroom full of people who succeeded. If you try to use this computation on a large variable, 我们现在的 n 是多少？128吗？ Yep. If we try to use 101以上, malloc doesn't work. The reason is because we have trouble packing the data so that your registers can grab it quickly. When we use SSE, here is our ALU. Here is our SIMD engine. SIMD engine is designed to go fast. Fast. When you're performing a job quickly, you're not very careful about the information you take in. So let's say you're working at a job where you have to stamp envelopes. You take an envelope and you stamp it and you pass it on. You take another envelope and you stamp it and you pass it on. You do it 1 million times. You're going to make mistakes. SIMD engine is designed to grab 1 million envelopes. It's designed to perform data or computations across millions of elements. It's designed to do this. It is not designed to check carefully to make sure it has correctly grabbed information before doing the computation. The only way to make sure that the data passed to SIMD is correct is by making sure that the way ALU grabs information from memory is well aligned with how the information is stored in memory. So when we allocate memory on the CPU, in the memory, we need to find a way to allocate it such that the ALU can grab it quickly. malloc does not care about the speed. malloc is a slow way of doing this. CUDA malloc does care a lot. CUDA malloc aligns memory in a way that allows its cache on the card to grab the information quickly, but malloc does not. So we need to find a better way. malloc, unfortunately, is not good enough for it. It gets to the point where if you have enough data, the ALU is going to attempt to take some data and it's going to pick up dirty data or pick up half a piece of data. When that happens, it's going to get a segmentation fault because it's trying to compute information upon incomplete data or broken data. It's a shame that none of you saw it today. It will happen if you start to use it for your research. So we best make preparations. You will get a seg fault eventually because you did not line up the memory in a way that makes it easy for the CPU to collect it. Because SIMD is designed for high speed, it will not check to make sure the memory is accurate before using it. Conventional computations do. If you're using normal code with normal malloc, whenever you copy information from memory into a cache for computation, the computer will perform a check to make sure that memory is correct before doing the calculation. The ALU will not do this for your registers. So we want to make sure it is safe. We align it properly. When I say alignment, I put the English here so that you guys can read it rather than listen to me talk about it. When I say alignment, I mean we align the information in such a way that every time the CPU memory controller goes back to memory to collect a piece of memory and place it in its cache, it collects a finite size of data, maybe 64 KB. If I don't align my memory properly, the first few KB are going to be half a float and maybe the last few KB are going to be half a float and you'll get whole floats inside. But if you align your data properly, in that 64 KB we're going to get 2 floats, 2 whole floats, which means to get 2 floats we only need to make 1 trip to memory. If we do not align our memory, to get those 2 floats you're going to need 3 trips. 1 trip to get the first half of the first float, 1 trip to get the middle of both floats, and then another trip to get the end of the second float. So by aligning memory in this example I just mentioned, in 1 trip to memory we get 2 floats compared to 3 trips. So by using aligned memory we increase our data access speed by 3 times, potentially. This is a substantial increase in performance because in many of our applications, the memory speed is our limiting bottleneck. And by using aligned memory, we go faster. Here's the code that you want to be using. Don't use malloc. There is another function that performs this task. He is a very good friend of mine. The Linux operating system was built on POSIX. We're going to go back, way back, and we're going to use the POSIX memalign function, which is a lower level alignment method for memory allocation. It looks a lot like, what does it look like to you? It looks like CUDA malloc. It's close to CUDA malloc. CUDA malloc was copied after this. So they write CUDA malloc in the way they did because it mimics this. Size T decides the alignment. You don't need to worry about that. Leave it at 32. And the rest is as you see it. I want you to go modify your codes, please, to remove malloc and start using POSIX memalign instead of malloc. Yep. 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 So let's see. 3 floats here, right? What you want is, here is the ALU over here. We want to grab one piece with one whole information and do the computation. But if you don't align the data properly, when I go back, I might only take this part. It's not a whole float. The rest of the information's here. So it realizes this. If you're using regular computation, it will go back and get this piece, plug them back together, and do the computation. That means 2 trips for 1 value.
So if you align, there is no way he will make a mistake.
That's right. Yep. Yep. That's all right. If you want to start using SSE2, SSE3, and everything else you saw, you need to do this first. Otherwise, you get massive faults. So from today's class alone, you should be able to increase your CPU code speed by 8 times with 1 core. You've got a chance to see that. That's what my code looks like. Instead of using special functions to allocate memory, I just put POSIX memalign at the start and at the end of my code. You don't actually have to create malloc functions. You don't have to create a function to allocate memory, just modify the malloc section in your code. What, to use functions? It's faster. It should be the same actually, because the compiler will identify it's a small function that doesn't do anything particularly special, so we'll cut and paste the source code in that function during compilation into the main section of the code. That's called inlining function, and most compilers will do this automatically. So the performance will be identical if the compiler is doing its job properly.
Are compilers still involved or is it just
Well, compilers have to decide whether or not to make it inline. They have to decide whether or not to cut and paste it back in.
it's still somebody doing compilers?
Yeah, it's a massive industry.
What's the difference between using GCP or G++?
One is for C, one is for C++. Yes, we can, yeah, because of the languages we're using, yeah. I would use G++. Easy peasy. 3 o'clock. Gosh, time flies in this GPU class. Feels like 10 minutes to me. Try to make sure that you get some good practice in using the object dumper and the deconstruction process. I want you to practice using that function there, objDump, deconstructing your objects and looking at that source code. I do want you to have some experience in reading the machine code, because only by reading the machine code are you going to really understand if your vectorization was successful or not. What are you reading about? Oh, POSIX memline. Yeah. There are other options. But POSIX memline came along a long time ago. All right, top it all. Let's get this show on the road. Code which uses POSIX memline like this should be faster. Even if you don't do the vectorization. Even if you just write normal code and your code does normal stuff. Let's say you don't want to use SSE, you don't want to use AVX, you just want to write a normal C code and hope the compiler gets it right. Using POSIX memline is still going to provide you a valuable result. It should increase the speed. Now, here's the kicker. I do not want to teach you SSE. 我没兴趣。现在没有人用 SSE. I want to teach you AVX. AVX is the son of or daughter of SSE. It is the offspring, it is the sequel. It is vastly improved, and you're going to see why. If we're going to use AVX, you must use POSIX memline. In the class we just had, you used malloc, and we used SSE vector intrinsic functions, and everything worked fine. It will not work fine with AVX. And AVX is the real gold mine. AVX, advanced vector extensions. Oh yeah, let's do it. SSE was used for many years, and successfully. It was so successful that they created many versions of SSE. After SSE came SSE2, then there was SSSE2, then there was SSE3, then SSE 4.1, then SSE 4.2. Oh my God. Intel eventually decided, working with AMD, to create a sequel. Why on earth did they do that? Where does the computational power come from nowadays? 你去买一个新的 CPU， 它为什么比你旧的 CPU 好？它的速度是一样 ，frequency 差不多是一样 ，number of cores might be different. The real increases in technology over the last 10 years are not related to frequency, and they are not related to core count. They are related to improvements in the ALU. When you buy a new CPU, you are not buying the improved frequency or the improved core count. You are looking for the SIMD capability of that chip. In 1998, or 1997, sorry, we used 64-bit registers. So that means 2 floats, or 4 half precision units. SSE, 我们开始用128 bits, so that's 4 floats. AVX uses double that. One AVX variable uses 8 floats, but we're not finished. This year's Skylake X chip uses 512 bits, 16 floats per cycle, which means if you go buy the latest Skylake X i7, it is going to run 4 times faster than this thing here, which uses SSE. It is a substantial improvement. The core count is the same, the frequency is the same, but the SIMD performance is much higher. This is the technology that we are trending towards. CPUs are not getting faster, they're getting slower. We are putting more cores on the CPU die, but as we put more cores on the die, we drop the frequency to make sure the total power is the same. We are improving the computational throughput of our chips nowadays by increasing the SIMD register. This is the direction that our technology is taking us. In the future, what can we expect? The number of cores will continue to increase. Their frequency will decrease to keep the total power the same. We can also count on the SIMD register width increasing. The next iteration will be 1000 bits, 1024 bits. So we're increasing the computational throughput on each core inside the ALU. We're not making modifications to other sections. Let's talk about AVX, because AVX was a massive hit. Before AVX came along, we were using SSE, and that was before Sandy Bridge, when Sandy Bridge Intel was released. Sandy Bridge Intel was the first one that used AVX, and the performance increase was staggering. It was astonishing, it was incredible. And everyone dropped the old technology so fast that nowadays everyone is using AVX. But there is a problem with this. The technology has changed so fast. In 1995, I was 15 years old, and I had a crush on a girl called Naomi Lee in my high school physics class. We created MMX. 1998, I was in uni. We had SSE. SSE survived a long time until 2012. In 2012, I was in 2010, sorry. No, 2012. End of Where's the data? It's going to be here somewhere. You can Google it. I was in Taiwan when they changed to AVX. How much time has passed? About 20 years in that time frame. In 20 years, the registered widths have changed from 64 to 256 bits. We've changed from MMX to SSE to AVX. Our cores have changed from 1 core to 4 cores to 8 cores. Have the compilers changed? The guy who wrote the GNU compiler in 1995 is still sitting in the same chair, still working on the same damn compiler. The technology is changing at a rate that is faster than the compilers are changing at. The technology is increasing so fast now that software and compiler technology cannot keep up with the hardware changes. This is a big problem for us. Let me promise you this. SSE was around for a long time, from 1998 to 2012. That's 14 years. In that time, we saw the compiler can write an SSE code, but it was ugly. It was horrible, but it did it. AVX was introduced in 2012. There is no compiler that can automatically vectorize into AVX. The compiler does not exist. Intel have released a new compiler that they say can do it. I've proven they cannot. Intel and I are not very good friends right now. But unfortunately for us, here's the situation. We need to write our own AVX intrinsic codes if we're going to use AVX. The good news for you is the code is identical to the SSE code. So if you can write an SSE code, you can write an AVX code. Remember, AVX 256 is AVX1, introduced in 2012, operates over 8 floating point operations in each cycle. We're talking serious improvements in computational throughput here. Massive numbers. So 8 times the performance, because in each operation it performs this. What does this really mean for us? The computer in my office has 16 physical cores. Each of those cores supports AVX, which means in each cycle we can perform in each core 8 times parallel computing, which means if I write my code properly using AVX and OpenMP, my speed up will be 16 times 8. What is 16 times 8? A big number. I don't feel like doing math. More than 100. By using OpenMP with AVX, I've made my speed up 100 times faster than a standard C code that uses O3 optimization. This is a massive difference. So you guys are doing your master's degrees and writing C codes. The code that you wrote last week is going to be potentially 100 times slower than the code that I'm going to show you next week. So we're talking substantial increases in performance. When you go to conferences, people are going to ask you if you got the most out of your CPU. I think now you have a chance. Because the compiler cannot do this. There's the AVX code. You know the drill. Save the SSE code you just wrote. Save a copy. Chuck this function in. This is the AVX code. It is virtually identical, but there are some subtle changes. You can make any name you like, man.
In the add function, it adds to the MM.
Yeah, that isn't necessary.
I forgot that.
While I was talking about that, did you just change them all to 256? Is that what you did?
Sure.
When I was talking about AVX, did you go and edit the code to replace? Yeah, it didn't work, did it? Yeah, you need to change the function. And that won't be the only thing you're missing either. And there's another one. Yeah. Yeah. I'm surprised you got your code to run. Did you try compiling it?
Just something here.
Yeah, just a few big freaking massive errors. I will show everyone how to fix those. There's nothing wrong. You typed it correctly. Your code's fine. There's something wrong with the compiler now. Since I'm here.
Oh, yeah, I also forgot the... Okay.
03?
Mm-hmm. Would it have changed something?
Yes.
Oh.
Fuck, you do it.
03, right?
03. No, big O. Big O.
Does it change?
Yes.
Okay.
Now you actually really do have a bug somewhere.
Weird, huh?
Oh. Actually, add IMM intern, please, as well as X. I haven't shown you yet. When you're done, show me. Your code won't compile. I have to show you how to make it compile. Your code doesn't compile. There are two things you need to do. Include IMM intern. 跟这个上面的一样，但是那个不是 X 是 I。Yep， 上面其他的都一样。Taking off? Okay, I'll be here. So, you need to add another include. And 那个 include 就是跟上面的完全一样，但是前面的 X 变成一个 IMM intern. Yep, but you also 你上面还有用 SSE 吗？还是你都有改变？那是你这里还是用 SSE， 所以上去。 你还是要加一个 x mm intrin， 所以就是 copy， 所以这个要变成 I mm intrin， but keep this, so write it again. Yep, 你有听到吧？ Add I mm intrin. So the same as this, 但是那个前面的变成 I. Don't remove that one though. Keep both. Keep both. 因为你的 code 上面还是用 SSE. That made it work, right, Alex? Yep.
So much faster now.
Yeah, you wouldn't know. Don't be sassy to me, son. You wait till it's a big code. It'll rock your... You do. You do need to include some other stuff. Yep, that.
Oh, that one.
Yep, that wasn't it. So, 还有一个另外一个工作.
This one.
Yep, save it. And exit. And now, when you compile, that's what you needed to include. You got a bug there.
Okay.
Yeah. What did you do? I think you did, but I don't know where.
What other things we need to include?
Hang on. I'm going to come over.
Oh,
Try again.
okay.
Not that. Oh, change your code to a CPP file, please,
Okay.
first, and then I'll come back. Now, sorry. Wait. Okay. All right, regular bug now. It doesn't know what AVXC is. 这个是小 C, 这个是大 C. Save and run. Show him. Did you guys figure out what you needed to do to make it run?
Change the header file.
Yep. To hey, wait. That's not the only error.
I've been running this file in another file.
Oh, go back.
Sorry.
That's all right. No. No.
That's it.
That's the first one, right?
Yeah.
Yep. Oh, far out. I'm going to execute someone. Yep, very good. And when we compile, we need one more flag. MAVX. You need to add MAVX. MAVX. Show me your code, man. Yep. Okay, exit out and save for me. Okay, and go to your compile line. And 03. Yep, and one more. You're good. Oh, all right. There are a couple of things you need to do to make your code run properly. Most of you should now be familiar with what I instructed you to do. You need to add immintrin.h at the top. You also need to add a new flag -mavx to your compile flag option. If you didn't catch that, put your hand up later, I'll come and we'll talk to you and I'll show you how to do it on your code. My code looks like this. You can see here, because my code doesn't use SSE, I took out my SSE and replaced it with an AVX function. So I only need IMM_intrin up here. I don't need XMM_intrin up here. I align my memory using POSIX memberline. Everything's sweet. I can use my AVX stuff. If you try to use the i03 compiler by itself, it will not work. You will need to add the mavx flag when you compile. The reason is because for the last 12 years, we have been using SSE. The GNU compiler assumes you are going to use SSE because it has been designed to use the SSE engine, and people are expecting it to continue to use the SSE engine. If you want to use the AVX directives, you're going to need to specify the flag specifically. Otherwise, it will not work. Let's analyze the changes. The AVX type is __M256, just like the SSE and the MMX type. If you go by an Intel Skylake X chip and you want to use AVX 512, what will that data type change to? Man, this is a fast class, isn't it? I can see people's brains ticking over. If I were to buy a new Intel chip, that would be 512, because the newest Intel cores use 512-bit vectorization. This is using 256, which we can use on today's CPUs. This is identical. We must divide by 8 now, because we're performing n on 8 loops, because each loop we pack 8 floats into our AVX array. MM256 for the add function as well. Nothing else to say. Now, let's have a look. Whew. Let's do it. By specifying the mavx flag, the compiler knows we are serious about doing the vectorization. We're not mucking around anymore. We type mavx. Do you guys understand what I'm saying? Okay, I'll continue using English then. When I compile and I add mavx, the compiler knows we are serious about vectorization. This is the compute ordinary function now. I want you to go into your code and check to see the machine functions, the machine code for your compute ordinary after you've introduced AVX. So for your AVX code, you still have a compute ordinary function. I want you to use O2 optimization, which optimizes for size, not for speed. When you do that, you can see the compute ordinary function has shrunken. Compute ordinary 没有用什么东西，它应该比较快。But 你要认真看，你不可以乱看，你要认真看。我们看一下 compute ordinary. It looks smaller. It is the worst compute ordinary code ever. Why is that? VADDSS is a sequential add. Each operation, the compute ordinary function is performing one addition. We place that operation in the SSE registers. You can see we use the XMM registers, so that's SSE. So we're copying our data to SSE correctly. This is because we're also packing the data properly. But SS is a sequential scalar operation. This is not parallel. We're putting our data into the ALU, and we're trying to use the SIMD engine. But each calculation, we're operating on one float only. Bad deal. This code is smaller than the last code we saw, but slower, because it is not in parallel. Here is our AVX code. How do you know that it works? Two things. VADDPS. PS is a parallel scalar operation, so it's parallel. And we are using the YMM registers. YMM. What the hell is YMM? Wiki tells us everything. Wiki has all the information you could ever want to know. 0 to 127, that is 128-bit. This register space is for SSE because SSE uses 128 bits and lives in the XMM registers. If we are performing successful AVX computations, we're living in the YMM regions because we're using this whole space. So you should see YMM appear somewhere in your source code, in your machine code. If you're using AVX 512 successfully, Z's. You should be seeing all Z's. So, check your objects. Use object dump, disassemble, deconstruct your objects, check to see the location of the registers which we're performing our computations with. If you're using XMM, it is at best SSE, at worst it is a sequential operation. If you're using the YMM registers and you're using the parallel scalar operations, PS, not SS, then you are performing parallel computations using AVX. The GNU compiler cannot automatically perform this vectorization. You can try and try as much as you like. Good luck with that one. We can see here the compute ordinary function is using VADD-SS, sequential using SSE registers. Otherwise, our AVX is using the YMM registers, and we're performing parallel add. We can see that by checking to see we're using VADD-PS. That's bad news, man.
I have compute SSE.
So that's, so this uses VADD-PS. Hang on, compute ordinary, son, not compute SSE. So we can see this uses VADD-PS on the SSE registers. This is using VADD-PS in the AVX registers. Go find compute ordinary.
Yeah, where is it?
There we are. VADD-SS. Yep.
Ah, sorry, I thought you.
That's all right. Show you another piece of magic. Saves the output to a file. All right, let's do it. With the information I've told you today, you should be able to use any modern CPU to increase the performance of any of your previous codes by 8 times. Every modern CPU you can buy uses AVX. Since 2012, they will use AVX. The GNU compilers and the Intel compilers will automatically attempt to use SSE, but now you have the tools to take advantage of the AVX technology which was introduced 6 years ago. Your prac. My favorite part of the day. I love Wednesdays during prac time. Prac. Last week you did the shallow water problem. It's a nice problem. We're not doing shallow water today. Shallow water is for civil engineers. We are mechanical engineers, baby. I don't care about water, I care about compressible gas. Today we're going to do a compressed gas simulation, which is called a shock tube problem. My students should know what this is. The other guys are going to find out pretty soon. We're going to simulate what we call a shock tube. A shock tube is a device we use in engineering to test hypersonic flows. We have a large pipe. At one end of the pipe, we compress a gas until the pressure is so high, it breaks a diaphragm. The gas then comes flying down the tube, flying down at hypersonic speeds. We see a shock wave. The shock wave, before the shock wave is a gas at rest. Then we have a shock wave caused by the high pressure that just was released. After the shock wave, we have increased density and temperature. After the shock wave, we have a contact surface. Contact surface plays the role of a piston pushing the gas along. After that, we have an expansion going back up to the original high pressure. I want you to simulate an explosion caused in a shock tube problem. That means the initial condition will look like this. We're going to have a pipe with a dimensionless length of 1. The first half of the pipe is going to have a pressure 10 times higher than the second half. So the ratio of pressures is going to be 10 times. Then we're going to remove the diaphragm that separates them, and we're going to let the gas go rushing down the tube. We should see all of the interesting features associated with compressible hypersonic flow: shock waves, expansion waves, contact surfaces. You may have learnt about these before. Aerospace students should have, but advanced studies in fluid mechanics will also investigate compressible gas flows. I'll give you the answer. Don't ask me if your answer is correct or I'm going to kill you. You guys can download my MATLAB solution. I've got a MATLAB code here. We're going to use the SHLL solver. Again, can you believe it? It's a useful solver. Last week you used the SHLL solver to solve shallow water. Today you're going to use the SHLL solver to solve gas flow, compressible gas flow with shock waves and expansion waves. If you don't know how to modify your code to solve for compressible gas flow, shallow water equation doesn't have an energy equation,它只有 mass and momentum equation. If we want to solve for the shallow water, the gas explosion problem though, we need to know what the temperature of the gas is. So we need 3 equations: mass equation, momentum equation, and energy equation. The equations are here. Go onto my website, look for my SODS 1D shock tube tutorial. You'll find the MATLAB code. Download my MATLAB code. Open MATLAB, run my code, get an answer. Then you have your answer and you don't need to ask me if it is correct. You can find this page by going to the parallel computing tutorials and download the MATLAB code directly. You will not find the link on my subject webpage. You need to go to the parallel computing tutorials. 如果你找不到的话，我就帮你找。Get the code. Download my MATLAB code, run it in MATLAB, show me your temperature. 我要看 temperature. 我刚才给你看的是 density and speed. I want to see your temperature. Then you need to modify your CPU code to solve the Euler equations. So last week you solved the shallow water equations. You need to add one more equation onto those equations. Once you're done, I want you to, if you look back, 我们的 FP 还有 FM 的计算, when we calculate the forward flux and the reverse flux in SHLL, these are vectorized SIMD computations. I want you to try to use AVX to parallelize these today. It is complex work. Good luck. The optional objectives. This is not so much optional. If you succeed, I want you to use object dump to make sure you're using AVX. You can check to see if you're using AVX because you can see if you're using AVX, you will see that you're using the YMM registers and you're using VAD PS and VMUL PS and all of the other parallel scalar computations. If you want, you can write a code which measures an increase in computational performance. It should be about, to be honest, 9 times faster. Does that make sense? AVX allows you to perform parallel computations across 8 floats, right? Why would the speed be 9 times faster? Because you packed the data, you aligned the data properly using POSIX memline. By aligning the data properly, the compiler is better able to predict which sections of memory are loaded and when, and you're able to get superlinear speed up through cache effects. So by doing the work I introduced to you today, you should be able to take the CPU code and accelerate it 9 times. Next week, we're going to then parallelize it again using OpenMP. Each core will use AVX, and so your total speed up will reach hundreds of times. Your performance should be approximately equal to the GPU code performance, but this code is substantially harder to write. Good luck. Go to that website, get my code.